Okay, so we continue with question 4. There's a dog pulling on a lead and there's a guy walking it. So basically the guy is walking along like this and the lead is like that at some angle to the horizontal, and here's the dog. And they give you two different angles and they ask you for the work done by the dog in each of the two cases, when this angle is only 15 and then when it's 40. So since he's moving in that direction, then the smaller angle means that most of his force is going to be going closer to the actual direction. So it makes sense that he does more work when the angle is smaller, and therefore the motion of his movement is closer, like more aligned to the motion of to the direction along which the force is acting. So hopefully that makes sense. His direction in this case is closer to the to the angle of the rope than if this was a bigger angle, right? So if the angle was like bigger like that, then this was 40. Then his movement is going in that direction, but the force is going in that direction. So they're not so aligned as here, so therefore the work done is going to be less, because when you take the cos product here, which is the force times cos of 40, that's going to be smaller than when you do the same force, which is 25 times cos of 15. You're going to get a bigger answer here. So that's the difference between the 240 and the 190 in terms of work. But you need to obviously multiply that by the 10 meters that he moves along, and you have the right answer for those. Then they ask you for the work that the person is doing. So he's basically applying the opposite force. So if the dog is pulling with 25, he's applying 25 in the opposite direction. And yeah, that's really Newton's third law. If the dog is pushing pulling on the rope, so that the rope is pulling in that way, with 25 newtons, then the person in his hands, he feels 25 newtons pulling him down 25 newtons, because that's the force that the dog is pulling with. But also the dog's gonna feel the 25 newtons of the rope from the tension pulling him backwards. Otherwise, he would just go off and speed off. But so he feels also the 25 newtons being pushed back. So in other words, the man is putting in 25 newtons, but he's putting them in the opposite direction in which they're traveling. Even though he pulls on the thing, they are still moving in that direction. So they're negative to each other, the directions. So it's going to be the same amount of work that the dog is doing, because if you still take the 25, you do cos of 15, you're still going to get the same answer when you multiply it by 10. Still get the 240, but now the movement and the force are in opposite directions, so you need to put in the 240 negative. So they want to check whether you understand there that the relative directions matter. Okay, so when you resolve his force, it's going to be this one here, and that's exactly the opposite to the direction of motion, so that's why they're negative. Interesting. Okay, can't rub that off. Okay, so let's move on quickly to question 5. Question 5. Draw a free body force diagram for a black block of mass 6 kilos, which is being pulled through a rough horizontal table 30 newtons. Maximum friction force which the table can exert is 20 newtons. Okay, so a free body diagram for a block of mass 6 kilograms. It's being pulled across a rough horizontal table, so let's see. So it's question 5. Here's the table, there's the block being pushed like that, 30 newtons, and there's friction of 20 newtons. That's nearly finished our free body diagram, except, of course, there is also the weight acting the object and the reaction. Right? All of those forces are acting. So it's 4. So that's friction, that's the force pulling it, that's weight, and that's the normal reaction of the table. It says says what is the work done by each of these forces in a horizontal displacement of 0.80 meters? So it's not bigger than that one. So it's going to be going in that well, it starts from 0, it's going to accelerate and move in that direction. It moves 0.80 meters, so that's 80 centimeters. So let's assume it's in that direction. So 80 centimeters or then what's the force the work done by each of these? Well, as we said before, what matters is the absolute force. It's not really the difference in the force. It's only when we're trying to calculate acceleration and resultant forces and things like that. But here we want the work done. The work done is just equal to the force times the distance. So you have to take each of those 4 forces and calculate the work done for the 4 forces. F1, 2, 3, and 4. Okay, so let's take F1 to be this one pushing forwards, 2 to be this one, 3 to be the weight, 2 to be the weight, and 4 to be the reaction. So the force work done by this one's easy, so 0.80 times 30. This one would be 20 times 0.80, but except you've got to look at, be careful because the guy's moving that way and forces in that way, so the answer needs to be for this one, for the friction. Work done by friction needs to be negative. Very often you work done by friction. What about these guys then? So 3 is the weight. So this distance, what is really important is that the formula for work done is the force in the direction of the motion times the distance. So the question is, what's the direction of the force? The weight is downward, and the direction of the motion is to the right. So in other words, the angle between the force and the direction of the motion is 90 degrees. Therefore, there's no work done. Whenever the angle and the motion, the force and the motion are 90 degrees, they're independent of each other and there's no work done. And if you want to check, normally you always do, if that's the force and this is the direction of motion, that's 20 degrees. And normally you do the force times cos, the full force times cos of 20, give you the answer. If you try that with 90 degrees, you get F cos of 90. You're going to get 0. It doesn't matter what F is, if the direction relative to the motion of the force is 90, then it's always 0. So no work is done by these guys. This one is perpendicular downwards and this one is perpendicular upwards. So the motion is completely independent to those 2 forces. In other words, this force is not going to help it go forward, neither is that one, or make it go slower. So they're both to do that. Yeah, makes sense? Next question is a little bit tricky, but a similar idea. So this is here. I can do this here, this other one for So let's see how we do this question. Let's choose a nice and visible color. Okay. So ski has been pulled up a 20-degree slope. So this guy here. This guy here is 20 degrees. And the wire is pulling with 15-degree angle with 320 newtons of force. The perpendicular contact force of the snow that happens through here, that force, they tell you is the normal, which is 620 newtons. And the friction force on the snow seems to go in the opposite direction to the motion. Friction force is 55 newtons, and the pull of the earth is right there, reacts here and something else, but with all things in front, 750 newtons. the force pushing forward, pushing 55 backwards, 750 down, and 620 up. So calculate the work done by each of the forces in this gear as she strikes 30 meters up the slope. So what's the direction of her motion? This one. Okay, and she's going to travel 30 meters. So similar to the question we just did, the question is, what's the force in the direction of the motion? Is there any of the following? If there isn't, the work done will be 0, and if there is, the work done will be the product. So I had some answers which are slightly different to these, but the idea is similar. They come out pretty similar anyway. But if you give the answers in kilojoules, anyway, we'll see what we get. When you subtract them all, I'll continue going through the question. So, part A, calculate the work done by each force. So, let's start with this guy. Okay, 320 newtons at 15 degrees. But we're interested in how much of those 320 newtons are going exactly along the direction of the slope, which is this guy here. That's the same direction, right? These are parallel to those. So we want to know how much of this is going in the direction of that. So that's 15 degrees. So the answer there would be 320 cos times 15. That would be how much is going in that direction. And that times 30 meters that she moves, that would be the answer to part A. Okay, what other forces are there? There's this force here, 55 meters. It's trying to go that way, but the thing is moving the other way. So 55 newtons times 30, but negative. That would be your answer to the second part. So that would be that would be the other bigger force than the negative. I'm guessing that would be this one. And then what are the other two forces? Where one goes down and the other one goes that way. We've done this in slopes before. If we want to know how much of his downforce is going along the slope, then we need to do one of those triangles. The skier is here, and the weight is in that direction. The weight is in this direction. And the slope is in that direction, which is the same as this direction, parallel to this perpendicular. Then this is 20, the same as this one. This one's 20. And so the opposite one that we're interested in, which is this component here of this force, is the whole weight of G sine theta. Okay? So theta was this one. Sine theta was this one. Sine theta tells you the component down the slope. So the component down the slope was sine of the weight. So yeah, if you do weight with 750 newtons times sine 90, then you get the force of the weight that is contributing in this direction. It's trying to make him go down the slope. So in other words, that would be the opposite direction to the weight that she's going. So it will also be negative. And should come out to be about this one. Okay, does that make sense? And then the final force that we have considered here is 620, which is the contact force of the snow on him. And that is exactly 90 degrees to the direction he's moving, so that's 90, it's going to be 0. None of the that force is going to have to go off keeping you from going into the floor. So it comes out to be 0. Okay, so hence show the total work done on the skier is 0, so then you have to add up all the work done on it, and then see that it gives you roughly 0. It won't come out to be exactly, but if you write it in kilojoules, then you'll see that you get like 0.0 something kilojoules, so that's roughly 0. Okay, and we run out of time with this question because it was quite a long one, so we'll continue with the next one.